we can start. Meanwhile, waiting for other people. And today we are glad to have Tianze to give us a JP seminar. I think most of us have known him. He did his bachelor at Peking University, and then he moved to Stanford, did his PhD. And since beginning of this year, Tianze became a Green Scholar and IGPP. So today, he will share us with his research. And the title of his talk is Imaging the Lithosphere with Virtual Deep Seismic Sounding. That's a cool part. Okay, Tianze, it's your turn.
Thank you. All right, let me share my screen. And so is it full screen now?
Yes.
Okay, great. Thank you, Shengguo, for the introduction. And you can probably see that I set my Zoom background at Stanford because most of the work I will present today are done at Stanford in collaboration with my PhD advisor, Simon Clempro, and many other people from all over the world. So let me put my cursor here. Traditionally, people use deep seismic sounding to study the interior of the Earth. And the way it works is quite simple. People typically deploy an artificial source, which can be just a big pile of explosive, a vibro-sized truck, or a simple hammer truck. Depends on how deep you want to look and the frequency component you desired. And those sources will generate downgoing waves, typically dominated by P waves. And those waves would hit interfaces in the Earth's interior and generate reflection waves, which will eventually be recorded on seismic receivers deployed on the surface. And with this method, people have been able to gain various insights of the Earth's interior. Here is an example of active source seismic reflection profile in the Tibet. This is the famous in-depth program on which you can clearly see the Moho of the downgoing Indian plate, as well as the MHT, the main Himalaya thrust, as well as those very peculiar bright spots at the mid-crustal level beneath the Tibet. And also, here is a more modern example of the application of traditional deep seismic sounding in the Aleutian Trench. And on this profile, you can clearly see those detailed features of the subduction zones. And obviously, this method has great success in revealing the secrets of the Earth's interior. However, it also has several very big shortcomings. First, it cannot see very deep because artificial sources are typically limited in their energy. Unless you use mini nuclear bombs like what the Soviet Union scientists used to do, you can't really see deeper than continental Moho. And usually the continental Moho is the extreme, the deepest part you can see with deep seismic sounding using artificial sources. And secondly, it's very expensive because you need a specialized crew who are licensed to operate explosives or vibro-sized trucks in the field. And that costs a lot of money. And finally, it causes damage to the environment. It's hard to imagine that you will be allowed to blow up the ground in the Yellowstone National Park. And to solve those problems, one very obvious way to go is to use natural earthquakes as sources. And it can successfully address all three challenges. First, because natural earthquakes usually have very large energies, they can see very deep. Essentially, with the appropriate distance and magnitude of the earthquakes you use, you can see as deep as you want. And secondly, it's much less expensive because you no longer need a specialized crews to operate in the field. You just need some inexperienced cheap laborers, also known as graduate students and postdocs, to deploy a bunch of broadband seismometers in the field in order to observe the signals you want. And finally, obviously, it doesn't cause any damage to the environment. So this is a very promising way to go. And this gives birth to the topic of my talk today, virtual deep seismic sounding. So we essentially add the one word virtual at the beginning of the word deep seismic sounding because we are using natural earthquakes to replace the artificial sources used in traditional deep seismic sounding in our method. Here is how it works. In our method, we use earthquakes happening very far away from our receiver, typically thousands of kilometers away. Here is our source, and it generates S waves, which travels across the Earth's interior and reach our station. We call it teleseismic S wave because it's S wave generated by earthquakes very far away. And these waves, when impinging upon the station from below, will interact with the discontinuities beneath our station. So we'll zoom into the area beneath our station to take a closer look. Here shows the area around our station, and we have the crust and mantle and the interface Moho discontinuity between them. And we have our teleseismic S wave, which comes up and hit the free surface. And that at that point, what we call a virtual source, that the upcoming S wave will convert to downgoing P wave, which will then hit Moho and be reflected upward. This phase, we call it SSPMP. And by comparing the travel time difference between this phase and the direct S phase, which we termed SS, we can constrain the thickness of the crust as well as the average property of the crust, very similar to what we did for traditional deep seismic sounding. And we call this phase SSPMP because it contains two SS lag, two S lag, and two P lag, and reflection and Moho, which we call it M. And typically we make this reflection a post-critical reflection in order to amplify the energy of this SSPMP phase. Here we have the name for the direct S arrival as well. We call it SS because it simply contains two S lags. And to make this post-critical reflection happen at Moho, we need to have a relatively wide angle of the incident P wave. And in global seismology, one way to measure the incident angle of a wave is by using term ray parameter, which is usually denoted lowercase p. And for the post-critical reflection to happen at Moho, we need the ray parameter p to be larger than the reciprocal of the p velocity in the upper mantle. Please remember this term because it will come back again and again in the later part of my talk. You may not be very familiar with the term post-critical reflection, but you must be familiar with the term total internal reflection in optics. Here is an example of the total internal reflection in which we have a laser beam incident from water in a water tank onto the interface between the water and air. And because when you have this incident angle sufficiently large, the essentially all energy of the incident laser beam will be reflected off this interface between water and air. And this only happens when you are going from a low velocity medium, in this case water, to a high velocity medium, in this case air. And if you flip this diagram, if you flip this picture, it will be exactly the case where we see in our virtual deep seismic sounding, because in the case of VDSS, the crust is a low velocity medium equivalent to water in this optic case, and the mantle is a high velocity medium, the same as corresponds to the air in our laser case. And because we're going from the low velocity medium to the crust to the high velocity medium mantle, when we have a sufficiently large incident angle, we can achieve post-critical reflection at the interface between those two media. Okay, so let's take a closer look at the kind of waves that can be generated in this setting. On the left-hand side is our ray path diagrams, and on the right-hand side is a synthetic seismograms generated by this simple crust over mantle model. And for the ease of showing the two relevant phases, we separate the synthetic recordings into S and P components with a particle motion diagram, particle motion analysis program. Here, S is shown in red and P is shown in blue. And the first feature we notice about this SSPMP phase is that it has a very strong energy because it underwent post-critical reflection and Moho. And secondly, we see a very peculiar phenomenon that SSPMP has a different shape from the incident S wavelet. And this is very different from other kinds of refraction phases because usually when you have a refraction phase, the shape of the wave packet should resemble the shape of the incident wave. However, because in our case, the reflection is post-critical at Moho, it introduces a phase shift to the reflection phase SSPMP, which alters the shape of the wave packet. And this makes it hard to directly measure the arrival time of SSPMP from the raw record. Instead, we have to match its phase shift in order to measure the travel time of SSPMP precisely. And in this case, by doing that, we can measure the phase shift of SSPMP to be 119 degree, and at the same time measure its travel time TVDSS at 6.95 seconds. And later on, we'll show that in phi VDSS, the phase shift, it contains a lot of information about the characteristics of the cross-mantle interface, the Moho. So I'm obviously now the first person who does research into the seismic phase. Previously, there has been some works on applying VDSS to various data sets collected over the world. And in the past, people have mostly used the travel time of the SSPMP phase to infer crustal properties. Here is one example in which people applied VDSS to the famous high climb transect across the Tibet Plateau. And on this one, they used the arrival time of SSPMP phase to infer a northward shadowing of the Tibetan Moho across its profile. However, they failed to account for one very interesting feature in their data, which is a rapid change of the waveform of SSPMP or phi VDSS in the southern end of the profile. Here we can see that the SSPMP recorded at the stations at the southern end of their profile has a significant negative side lobe following the prominent positive peak. However, in the rest of the profile, you don't see this feature. But in their paper, they didn't really discuss this feature. And here's another example of how open questions were left by previous VDSS studies. This is another seismic transect in northern China, which cross a region called the Ordos Plateau. In the background, the color panel shows the image created with P receiver function, which is usually regarded as the standard way of probing crustal structures. And the red band on this color panel is interpreted as the Moho shown on the receiver function results. And the black dots here are the VDSS Moho across this profile. And we can clearly see that along at the center part of this profile, the VDSS Moho has around 20 kilometers discrepancy from the receiver function Moho. And this actual layer of crustal material is interpreted by the author as a lower crustal, as a mafic lower crust that has survived since the Archean age beneath this stable Ordos plateau. However, there's also another possibility that this discrepancy might be caused by some artifacts in the VDSS methodology that we didn't previously know. Therefore, it is still there are still a lot of intricacies in the VDSS method that needs us to do more research on. So let's take a closer look at the phase shift of SSPMP, because this is a very interesting feature that is not present in other reflection phases. Let's do a small mental exercise here. Here, let's assume an instant wavelet in the shape of first derivative of a Gaussian wavelet. We assume this input wavelet because it resembles the observed source wavelet of many deep and intermediate depths teleseismic events. And when we apply a 90-degree phase shift to this anti-symmetric wavelet, what we get is a symmetric function that resembles the shape of a Mexican hat. And when we further apply additionally 90-degree phase shift, we'll again get an anti-symmetric wavelet, which is simply a sign flip from the input wavelet. And I hope you can bear those features in mind, because those are very important for you to understand the later part of my talk, which is about different phase shifts applied to the direct SS arrival. Okay, so we want to know how phi VDSS is controlled by different parameters along the ray path of our SSPMP. And the instinctive guess is that it must be controlled by the velocity across the Moho, because this post-critical reflection happens at the cross-mantle boundary. So we did some tests with 1D models. And for now, we'll assume that the Earth is perfectly 1D, and we'll leave the discussion on effects of 2D variation to the later part of my talk. Here, the models we assume has uniform velocity for the upper crust and the lower crust, but various velocity in the upper mantle. Here, we compute different synthetic waveforms for SSPMP for different upper mantle velocities. And the blue model in this plot corresponds to the blue waveforms here, and the green model corresponds to the green waveforms here. We see that as we increase our upper mantle velocity from blue to green, we observe a decrease of phi VDSS or SSPMP phase shift in our output synthetic waveforms. And this seems to suggest that phi VDSS is negatively related to our upper mantle VP. And we care about the upper mantle VP because it is a very important feature that can help us infer the property of the upper mantle. And we did a further set of synthetic tests with a higher ray parameter, which causes the reciprocal of the ray parameter 1/p lower. In this case, we still observe a negative relation between phi VDSS and upper mantle VP. However, it seems that its effect on the waveform becomes less significant than the case where we have a low ray parameter. This seems to suggest that ray parameter also plays an important role in the relation between phi VDSS and upper mantle VP. So we decided to conduct a more comprehensive test on the effects of those parameters. Here, I'm computing phi VDSS for various different values of the upper mantle VP and lower crustal VP for a fixed rate parameter of 0.125 second per kilometers. And in this plot, blue means high phi VDSS and red means low phi VDSS. We observe that indeed phi VDSS decrease with increasing upper mantle VP. And when the reciprocal of the rate parameter is very close to the upper mantle VP, for example, at the bottom part of this panel, it's almost completely determined by upper mantle VP, as evidenced by the subhorizontal contour lines. However, as we further increase upper mantle VP, making it further away from 1 over P, this is dependence on the dependence of phi VDSS to lower crustal VP gradually grows. We also compute this phi VDSS for a higher rate parameter, P equals 0.13 second per kilometers. And in this panel, we first observed that in general, phi VDSS decrease as we increase rate parameter, and also its dependence on the upper mantle VP decrease as evidenced by the more oblique contour lines compared to the left panel. So our conclusion is that phi VDSS is controlled by upper mantle VP only when 1 over P is close to our upper mantle VP. Therefore, if we want to infer the upper mantle VP from our observed phi VDSS, we have to choose our rate parameter to make it fall in the range of this part where 1 over P is pretty close to our upper mantle VP. Now that we know the relation between phi VDSS and upper mantle VP, we want to see how we can infer the upper mantle VP from phi VDSS from observed data. So we did some further synthetic tests. Here we generate SSPNP waveforms for a wide range of rate parameter P. And again, we are showing P and S components separately. And on this panel, we can clearly see a change of phi VDSS as rate parameter changes. And we also see a change of a T VDSS or the arrival time of SSPNP with rate parameter, which we call a move out. Later we'll show that both information can be used to infer the property of the crust and upper mantle. And as we mentioned before, we can fit the SSPNP waveform in order to derive phi VDSS and T VDSS. Here is an example. The blue one is the observed P waveforms, and the black one is the best fit one. From this waveform fitting, we can get our T VDSS at around 7 seconds and phi VDSS at 130 degrees. We further plotted as a function of rate parameters, and we clearly see a decrease of phi VDSS with increasing rate parameters. We then computed different relations between phi VDSS and the rate parameter P, which are plotted in red here. And by comparing the observed and observed data and the theoretical curves, we can clearly see that the observation prefer an upper mantle VP of 8.1 seconds per kilometers, inconsistent with our input model. And also we can plot the function of T VDSS of rate parameters. And it also shows a decreasing trend of T VDSS with increasing rate parameters. And this is what we call the move out again. And using a linear regression method, we can use this information to constrain the average crustal VP to be 6.5 kilometers per second and the average crustal thickness of 40 kilometers. Those again in good agreement with our input model. So this is how, so this synthetic test show us it is possible to use observed phi VDSS and T VDSS to constrain upper mantle VP and the crustal average VP and crustal thickness. Now let's see how it applies to real data. And we choose the Yellowknife array sitting at the Slave Craton as our field example because it has several advantages. First, it is a permanent array that has very long recording time, which gives us a lot of data to choose from. And secondly, it's in the correct range from the high seismicity from the Western Pacific subduction zones, specifically the Kurile Islands and the Kamchatka, where we can see, where we have very rich, deep and intermediate earthquakes. And finally, it sits at the stable Slave Craton, which is one of the oldest pieces of continent on the Earth. And another interesting thing about Slave Craton is that the oldest rock that has been found to date, the Akasa gneiss, was found at the Slave Craton with an age of around 4 billion years. And also this stable craton make it appropriate to approximate the structure beneath our station as 1D. So our previous methods can be safely applied. Here is a zoom in view around our station. This triangle is our recording station, and the stars are the virtual source locations of the events we use in our analysis. And the red dots are the reflection points of those events. One additional advantage of our recording geometry is that in addition to the long-standing permanent YKW Yellowknife array, and the YKW3 is a component of that array, we have additional array EDZN, which is a part of the Canadian temporary deployment called Polaris. The advantage of having the station EDZN is that we can compare the receiver function recordings at station EDZN with the VDSS recordings of station YKW3. This is because for receiver functions, the Moho piercing point is usually quite close to the recording station. Therefore, we can treat the receiver functions recorded at station EDZN as seeing the same crustal structure as the VDSS recorded at YKW3, because the VDSS reflection points are very close to the station EDZN. And finally, we also have the Canadian lithoprobe active source project running almost in the same region as our passive seismic recordings. And this offers us an unprecedented chance to compare passive seismic results with active seismic results on their resolution of crustal structures. And here are the events we use for our VDSS analysis, and they are sorted by increasing rate parameters. Again, we can clearly see a decrease of SSPMP arrival time, or TVDSS, with increasing rate parameters. And we apply the waveform fitting procedure as described before to extract the arrival time and phase shift of SSPMP. We again plot them against the rate parameters and compare them with different theoretical curves. And this comparison clearly shows that our observed results prefer upper mantle VP of 8.0 to 8.1 kilometer per second, which is consistent with the result given by the active source studies. But of course, the real data is much noisier than our previous shown synthetic data. So we can't have as well constraint as in the synthetic case. But we still can confidently say that upper mantle VP of 8.0 and 8.1 kilometer per second is preferred by our data. And at the same time, we can plot our observed T VDSS as a function of rate parameters, and use the same linear regression method to derive average crustal VP and crustal thickness, which are both higher than previous results given by active source studies. And this is interesting because obviously we are seeing the same Earth, so different results should show consistent results on the different method should show consistent results on the same object. But in the contrary, they don't. So we decided to look deeper into this. The way we did it is to see whether the receiver functions recorded at station ETZN can offer us additional insights. So we compute receiver functions at station ETZN and combine them with the VDSS recorded at YKW3. Because VDSS at YKW3 can give average crustal VP and crustal thickness in this area. Therefore, by incorporating those information into the receiver function observation at ETZN, we can further derive the average crustal VP VS ratio. And here I'm plotting a joint probability density distribution of those two parameters, which clearly shows the trade-off between those two parameters. And this trade-off is very clearly to be negative in our case. And this result becomes significant when we compare it with rock physics results. Here I'm plotting a scatter plot of silica content of rock samples with different silica content and their corresponding VP VS ratio and average VP compiled by Bradley Hacker in his 2015 paper. And in these rock physics results, we can clearly see an increasing trend of both VP VS ratio and VP with decreasing silica content. And in another word, as rocks become more mafic, they become higher in both VP and VP VS ratio. And this trend is orthogonal to the trade-off between our between our average crustal VP VS ratio and average crustal VP. Therefore, despite the relatively large uncertainty in our result, we can still tightly constrain the average crustal composition to be intermediate. To further confirm our results, we also compare it with another set of rock physics results, which is a classic rock physics results compiled by Christensen in his famous 1906 paper. And in his result, it also shows a clear increase of both VP and VP VS ratio as his rock samples becomes more mafic from granite at one end to gabbro at the other end. Therefore, this comparison with two rock physics examples clearly indicate that our results can tightly constrain the crustal average composition in this area to be intermediate. This result is important because crustal average composition is closely tied to the forming mechanism of crust, especially in the Archean. And people have been speculating whether a crustal forming mechanism is changed from plume dynamics to plate tectonics after the initiation of plate tectonics some point in the Archean or the early Proterozoic. Therefore, our results can potentially offer more insight at the timing of the initiation of the plate tectonics in this region. And if you apply this to other cratons in the world, we can probably see a more clearer picture about how the plate tectonics initiate at different parts of the world. And in comparison, the lithoprobe active source projects put their average crustal VP VS ratio and VP at a very different composition from our results. Their results clearly show a more felsic composition than ours. So to further distinguish our result from theirs, we decided to constrain the average crustal VP-VS ratio with the additional method, which is a classic HK stacking method used to analyze receiver functions. In this HK stacking method, people use not only the primary PS conversion and Moho, but also the Moho multiples arriving after it to constrain VP-VS ratio from receiver function studies only. So this is a completely independent observation from our joint receiver function and VDSS analysis. We applied this method to the receiver functions recorded at station EDZN and get very similar results from what we get from our joint analysis. And when compare those two results, we can see that they agree very well within the uncertainty range of each other. And this further proves that our results is superior to the ones offered by the active source experiments, because our results are consistent across different passive seismic methods. And here is a summary of what we learned under our 1D approximation. First, VDSS can give us uppermostmantle VP. And secondly, a joint VDSS-P receiver function analysis can tell us about the average crustal composition in our study area. And finally, the southwest South Slave Craton has an intermediate average crustal composition. Now, after we have learned our lesson in 1D, let's move on to 2D, because obviously in most parts of the world, the structure cannot be well approximated with a 1D layer structure. And the first thing we want to see is why 2D variation matters for our analysis. So here is our ray path diagram again. And one important feature of our VDSS method is that it's a wide angle method. In VDSS, in order to achieve post-critical reflection and Moho, our virtual source is typically very far away from our station. And for a typical crustal thickness of 40 kilometers on continents, this distance can be up to 120 kilometers. And this makes it possible to some velocity anomalies to exist on the ray path of the SS wavelet of SSPMP, which does not exist on the ray path of direct SS. And if this is the case, then the travel time anomaly caused by those velocity anomalies will be included in the observed travel time anomaly of SSPMP phase. However, if we analyze the waveforms assuming a 1D Earth structure, we will introduce artifacts in our resulting Moho depth estimates. Here we use a 2D synthetic test to further illustrate this. This is our simple velocity model in which we have a uniform crustal thickness across the model. And below this uniform crust, we have a strong variation of mantle lithosphere, which resembles the case of a stable craton embedded in two actively extending areas. In this case, we expect VDSS to see a uniform Moho depth across a profile. However, the synthetic waveform show a very different picture. Here we are lining all the traces on SS arrival, and instead of a uniform SSPMP arrival time, we are observing a delayed SSPMP arrival on the western end of the stable craton, but advanced SSPMP arrival on the eastern end of the stable craton. This is because for the station at the western edge of the craton, the SS lag of SSPMP travels through more low velocity asthenosphere than the SS arriving at the station. This causes an additional delay on the SS lag of SSPMP. And this further delays the SSPMP arrival. On the eastern end, the cause is exactly the opposite. So if we ignore the potential effects of the sub-Moho velocity structure to our SSPMP arrival time and simply infer Moho depths directly from our observation, we'll end up finding a deeper Moho at this end and a shallower Moho at this end. So this is a very challenging situation for the VDSS analysis, but fortunately we have found a way to address this problem. The principle is very simple. If we have a station at the location where the virtual source locates, then we'll be able to directly see the travel time difference between the virtual source and the station. And by incorporating that into our analysis of SSPMP arrival time, we will be able to account for the velocity variation along the array path. Here, again, we use a synthetic test to demonstrate our method. In this test, we are using a sinusoidal variation of the lithosphere asthenosphere boundary below the Moho to approximate velocity heterogeneity in the mantle. And we again use a plane incident wave that starts at the bottom of the model. And here is the data recorded on the dense array we assume at the surface. And we can clearly see that despite the flat Moho in this model, we see a variation of SSPMP arrival time across the array, which is obviously caused by velocity variation below the Moho. And this is further shown by the individual traces recorded at those stations. However, in this case, we have SS arrival time anomaly information across the whole array. Therefore, we can incorporate that information into our ray tracing scheme that can account for this variation in velocity structure beneath the Moho. And by applying this ray theory-based backprojection method, we can recover the flat Moho geometry despite this strong variation of velocity structure beneath the Moho. Here is a zoom in view of our Moho model. And the black solid line shows our corrected Moho, and the dashed line shows the Moho without our travel time correction. And in this case, those two don't differ very much from each other because the velocity variation beneath the Moho is not strong enough. However, if we decrease the wavelength of the sub-Moho structure variation to 400 kilometers, this difference becomes much more pronounced. So this is a case showing that we are able to account for sub-Moho velocity variations in our back projection scheme. Then what about variations, lateral variation in crustal thickness itself? So we conduct additional tests with a variation of Moho depths across the array. Here, the Moho depth varies at a wavelength of 400 kilometers. And in this case, the situation is even more challenging because the Moho depth change has effect in both the SS travel time and the SSPMP travel time itself. However, with our ray theory-based backprojection method, we can still retrieve the Moho topography relatively well compared to the dashed line, which shows the Moho depth variation without any correction. And an additional thing what I want to note here is that the amplitude of SSPMP changes very rapidly. In this case, with undulating Moho, which can be a very useful diagnostics for Moho undulation in future field observations. And finally, we combine both Moho depth undulation and LAB undulation in our model. And in this very extreme case, although our results don't recover the Moho geometry very well, it is still significantly better than the uncorrected one, which is shown as the dashed line here. And in this case, the variation of SSPMP amplitude is even larger across the profile. Finally, let's see how this applies to field data. Now we are coming back to our initial example, which shows a very different VDSS Moho depths and receiver function Moho depths in the Wardles block in North China. And people want to study Wardles block because it seems to be the remnant of the Archean North China Craton, which underwent significant modification during the Mesozoic, a process also called decratonization, whereas the Wardles block stays stable over those period. Therefore, people want to understand what makes the Wardles block survive this intense period of modification. And in this previous publication by Yu et al. In 2012, they use a linear array across the east boundary of the Wardles block. However, because their earthquakes are coming from the south, it's impossible to constrain the effects of the lateral variation because their virtual source are outside their profile. However, and the circles in this diagram shows roughly the region where they observe the over-thickened lower crustal layer. However, with a new data set, well, it is possible for us to apply our method. This is the China Array project, a Chinese effort to emulate the US array with the goal of eventually covering the whole China with dense broadband seismic array. And this array record the earthquake very close to the events used by Yu et al. In 2012. Here, the color shows the travel time residuals of this event on those recording stations. Blue here means travel with advanced SS travel time, and red here means delayed. And there you see this cluster of advanced travel time, SS travel time at the northern Wardles block, because there is a high velocity lithospheric queue exists beneath the Wardles block, which advance the SS arrival time in the area in the northern part of the array. And obviously, this strong variation in velocity structure will have strong effects in the SSPMP travel time, which is not fully accounted by the previous study. From this 2D array, we extract a linear line to make our profile, which is shown here. The line crosses the actively extending Weihe Graben and the southern and central part of the stable Wardles block. Here, I'm showing the S component and P component recording along this array. And from the aligned records, you can clearly see an increase of SSPMP arrival time as we go north along the profile. And if you convert those SSPMP travel time measurements directly to Moho depths, you will see almost doubled Moho depths from the Weihe Graben to the stable Wardles block, which is essentially what the previous authors see. And this is an uncorrected image computed with the data along this profile. And I'm also showing the result from the previous authors. The gray ones show, the gray diamonds show the previous VDSS Moho depths, and the gray dots shows the previous receiver function Moho depths. And this uncorrected image clearly agrees pretty well with the uncorrected results from Yu et al. 2012, whereas the previous receiver function results agrees pretty well with the newer receiver function results that are derived from this newer and denser array. However, after applying our correction, which is shown in this black solid curve, we can see that the Moho depths in the central part of the Ordus plateau become significantly shallower than before the correction. And after the correction, the VDSS Moho depths agrees significantly better with the previous receiver function results. And what I want to know is that different receiver function results still give different results in this area, because first is overlain by a pretty thick sedimentary layer, which are known to cause severe problems to both receiver function and VDSS. And secondly, this area probably has a much more complicated, deeper crust structure than many other parts in the world. So our results is pretty promising, although it didn't completely eliminate the difference between receiver function Moho and VDSS. We are pretty confident that our results is better than the previous VDSS Moho image, because our results correctly account for the effects of a lateral velocity change along this profile. This actually makes a very smooth connection to what I'm doing now here at IGPP. Here I'm showing my PhD project, which is applying a part of my PhD project, which is applying VDSS, a kind of passive seismic reflection method, to the China array data. And my postdoc project here is very similar, except that I'm using a slightly different method and applying it to the US array data. For my PhD work, I'm using a method developed by Peter here at IGPP called the long period S reflection, which instead uses the pure S reflection to image uppermostmantle discontinuities, in contrast to the Moho in VDSS. And but both methods fall into the broad category of passive seismic reflection seismology. And in general, I see this field as a very promising one, and there are still a lot of new discoveries waiting for us to make. With this, I would like to conclude my talk with those summaries, and I'm ready to take any questions from you.
Okay, thanks, Tianze, for your interesting talk. And we still have a few minutes for discussion. If anyone has questions, just speak out.
Oh, Ignacio is raising his hand.
Yeah.
Ignacio.
So, Tianze,
yes.
You know that in the last month with Jennifer, we have been working with GNSS reflections, in which basically we are trying to take advantage of reflected waves in order to get some properties, for example, from the sea level. And what we discovered in a couple of weeks ago is that when you start to play or start to analyze the diffusive reflection, the diffusive reflection is when you are very close to the critical angle, and you start to miss the specular reflection, the nice rays that you get after bouncing and getting from your instrument. But the diffusive reflection, which is very close to the critical angle, seems to have a lot of information related with the roughness of the safe surface where you are reflecting. So I was wondering when I was listening to your talk, maybe it would be cool to see what is happening when you are very close to the critical angle and see if you actually can see diffusive reflection and try, for example, to infer what is the small scale roughness of your Moho or any layer that you may have beneath. So that is the question, idea, or I don't know.
Yeah, right.
Yeah,
I totally agree with you. I think so. There are still many unsolved puzzles revolving around this phase, because one observation we have is that this phase, so ideally this phase should always be a strong phase because it's post-critical reflection. So no matter the interface is a sharp interface or it's a gradient zone, this post-critical reflection should always be strong. However, the reality is that we don't always see a strong reflection. In fact, in many of the events, we don't see a very strong reflection. Let me go back to the one where I showed the field example. So here, the reason that I only show a handful of events recorded at the Yellowknife array is because those are the only high quality events we have. So so many of the events, we don't have a very strong SSPMP arrival after the SS, which is very puzzling. So I have been wondering whether that can be related to the roughness of the Moho in this area and also in other areas as well.
Yeah, what I understand is that as long as you are increasing that angle or you are increasing the distance from the reflected area, your incidence angle start to be smaller, and by that means you expect to see an apparent smoother surface where you are reflecting. So I would think that if you get farther from the reflection source, you would be able to see a clearer signal from the reflection. Or at least in the GNSS thing, that is what is going on. When we are using very, very shallow angles, you can see a very nice specular reflection when you are getting far away from the receiver.
Oh yeah, right. So you are talking about the EM waves reflected off the sea surface, right?
Yeah.
Yeah, but I think they should have very similar behavior as the mechanical waves in seismology. Yeah,
That
so I
is
think that's a
what
very
I'm
good
thinking.
point. Yes. Yeah, I'm planning to probably look deeper into this somewhere in the future, but obviously I have to take care of Peter's business most of my time now. But this is definitely a very, very interesting thing to dig into. Thanks.
Interesting. Thank you, Tianze.
So the time is about up. If we don't have any more question, and probably we should thank Tianze and also thank for everyone participating, and see you next time.
Sure, yeah. Oh, I saw David is clapping. Thanks.
David is talking. Yeah, okay.
Yeah,
Some real claps.
Thank you. Right. Yeah, next week we'll have another speaker at the same time, and hopefully everybody will stay up to it.
Yep.
Thank you. See you guys.
Thank you, Tianze.